Let's talk a little bit about streams and flooding. It is a natural feature of streams to flood sometimes. You have different kinds of floods in different places. In the upland streams, the headwater streams, you often have flash floods. The drainage area gets some water dumped on it by a big thunderstorm, and suddenly those streams are flooding. This also happens in even dry areas. And you gotta watch out for those flash floods if you're in the desert and it's raining just dozens of miles away even. Floodplains can also be covered in big floods in meandering streams. And it is important to note that human activity can affect the severity of floods when they occur, but they can't totally eliminate floods altogether. Floods are often classified based on local morphology and climate, and they are given a probability of occurring in any given year usually. And then they are assigned a recurrence interval based on that. So for example, in any given year, a particular flood in an area might have a 20% chance any given year of happening. And because it has a 20% chance out of 100%, that's 1 in 5, they're going to be called 5-year floods. Doesn't mean they happen every 5 years, but it means that on average, they'll happen every 5 years. 1% chance, that's 1 in 100, those are called 100-year floods. So a lot of times when we're dealing with flood zones, we might be dealing with 100 or 500-year floods. 100-year floods have a 1% chance of occurring any given year. 500-year floods have a 0.2% chance per year. They can happen. They don't happen every 500 years. Often, if you graph the discharge versus the recurrence interval, how often they happen, and you do it on one of these linear and log plots here, you end up with this straight line. Don't worry too much about the math, but do know that we can use the plotting of the types of floods and how often they occur to predict floods we haven't even seen yet, like the 100-year floods. That would probably have a discharge around 25, 26, 2,700 cubic meters per second, and they have about a 1% chance of happening in a year. We extrapolate that based on the data that we actually have for these floods. The recurrence interval is the approximate amount of time on average that it's going to happen between floods of a certain discharge. Doesn't mean that they happen like that all the time, or that it happens regularly every certain amount of years. That's important to note. That is, the time between 100-year floods is not necessarily 100 years. So here's a graph where we're looking at the discharge of the largest flood that year in a particular river, and the year over here. So real reliable data started here in maybe 1860, where they were measuring every year the amount of discharge from this river. And they had one of their 100-year floods in 1903. The next time they had a 100-year flood was 1993, 90 years, close to 100, but not necessarily. And if you went back in time to here, you would see that that was only 59 years there. But on average, that 100-year flood is going to happen about once every 100 years, provided that we haven't changed the local climate or the local topography or the type of runoff too much by urbanizing. So those things will affect the recurrence of things like 100-year floods too. And it's often very difficult to predict what exactly those effects are going to be. You can know the direction that they're going to move. If you urbanize an area and cover it in asphalt, a lot of that runoff is going to happen a lot faster and you can get bigger floods. How much bigger? It can be a little hard to predict. Flash floods are the name for any sudden flood. They naturally occur in dry places. They naturally occur in steep places. They can also occur for human-created reasons, right? If you have a dam and that dam collapses, suddenly you have a flash flood now that is not any longer being held back by the dam, that's moving very fast downstream. And this is the source of some of the biggest losses of life in disasters and in US history. For example, the Johnstown flood that I'm remembering in Pennsylvania killed 2,000 people. The creation of impervious surfaces by humans can also promote these flash floods because runoff can happen off asphalt, concrete, much faster than it can happen off of natural soil where water will percolate downward first. So that flood just moved a lot of water very quickly. And what's more, if you notice the size of some of the particles that water was moving, some of them were boulder sized, car sized boulders being moved by this sudden flood. That's why you don't build your house in a mountain valley channel, because when it does have a flash flood, that's what it could look like. We can look at this graph called a hydrograph to think about the effects of human changes on the amount of discharge over time and the type of flood that we end up having. So a hydrograph is a graph of discharge over time. So after a rainfall event, in any natural stream, you're going to increase the amount of discharge shortly thereafter. It takes some time, though, between the rain and the water to actually reach the stream and start flowing through it. This is what it would look like in a forested watershed before urbanization. There's some delay, and it's a spread out peak. After you reduce the forest, add buildings and roads and a lot of impervious surfaces, the runoff can reach the river much faster, and it all tends to reach it more closely spaced together in time, which means the flood happens faster, the flood is also larger, the discharge ends up being much larger. The flood does also end sooner, but the real damage comes from the fact that the discharge is so much higher than it would be under natural conditions. Here's an image, little diagram of a natural floodplain, which we know naturally floods in a meandering river. And as we see on this diagram, this area has been extensively farmed. That soil that's being regenerated by the periodic floods is naturally very fertile. But if you build your houses and farms down here, you are putting them at risk, because when it does naturally flood, this whole area is going to be inundated with water. This isn't really something that we can eliminate completely as humans, nor would we necessarily want to, because it's really what keeps these floodplains so fertile. Flooding in floodplains like this can cause a whole lot of damage, though. For example, this is a satellite image of the floodplain of the Mississippi and Missouri rivers in '93, and a major flood that happened there, not from a hurricane, but just from large amounts of rain happening upstream. And it took 2 months, but over that time, 400% of annual rainfall fell. So 4 times the normal amount of rain that fell in a year happened upstream of this in only 2 months. So as a result, in a city like St. Louis, right on the Mississippi, the water actually crested 47 feet above typical flood stage, caused dozens of deaths, thousands of homes lost, billions of dollars in damages, all because people built in a floodplain because it's a nice flat place to build, and you've got lots of good farming opportunities there. It is a risk that you take when you build in a floodplain. This Johnstown flood that I had mentioned was a dam failure in Pennsylvania. Who was it? I'm forgetting. It was like Andrew Carnegie or Mellon or Rockefeller, or one of those folks had built this dam up here as to hold back a lake to have like this nice resort area. And then there was this mill town below it, Johnstown, but the dam failed. And as a result, it temporarily released discharge equal to the Mississippi River. It picked up whole houses, whole buildings, and just blew them away. It killed 2,200 people, all because we built a faulty dam. How can we mitigate damage from floods? One of the ways that we can do it is by replacing some of our impermeable surfaces, regular asphalt, with permeable ones that have some porosity in them that allow some of the water to flow directly into the ground that normally would do so. So here's an example of some of that permeable concrete. As a result, that soil can take up some of the water. It slows it down. Much of it will still eventually reach the stream channel, but it does so much slower and in a much more natural way, which helps reduce the overall magnitude of the floods. We can build, and we often do build, artificial levees, artificial dams that hold back the sides of the river. Rather than a dam that sits and runs across a river, levees are these mounds that run along the side of the river. So some of them can be natural, like we saw, but some of them are artificial. The thing that they do is they just send the flood downriver. When the flood water rises, it prevents the flood waters from cresting over that levee. And so it keeps this area dry, but it just sends all this water further downhill. So if you build a levee, your downstream neighbors might not be too happy with it because it just means they're getting the water that you didn't. They do have a failure risk associated with them, though. If they do get breached, they are going to breach in a massive way, and it's going to quickly, positively feedback, accelerate, and then you have a sudden flash flood instead of just a typical slow-moving flood. Here you can see that artificial levees can also work on a really small scale. So here, the water level is held back by this big, thick levee and actually protecting this whole house, which is kind of cool. But you can see that they have some concern that they've laid down with sandbags, thinking that this is the point at which it might breach. And if it does, they're getting a flash flood and their house is totally destroyed. So dams are another way that you can mitigate floods downstream. They also provide things like power if you build them a certain way, and they can hold water in reservoirs, and they can provide nice open lakes for recreational activities. They help moderate small floods because you can control the amount of water that's running through them at any given time. And so in advance of a big rainstorm, for example, you can start to let extra water through, knowing that you're going to have to trap more water behind the dam when the rain actually happens. But they do provide some failure risk. So you have to do really good engineering to make sure that these dams are going to last for a long time. So for example, we can take a look at this Fort Loudoun Dam. And if this Google Earth link works, that would be great. So here we can see the Fort Loudoun Dam and what it's holding back near Lenore City. And we can see that it's artificially made the water surface much higher up here than it is downstream of it. See, it drops by dozens of feet there. It's pretty cool that you can see this even just looking on Google Maps. Okay, folks, thanks for listening to this lecture. I will see you online.